All right, let's get into it. Today we are going on a pretty wild journey. We're going to start with literally a grain of sand and end up with the colossal planet-sized brains that are powering all of modern AI. It's an incredible story, so let's just dive right in. So here's the big question, right? How do you build a brain out of a rock? I mean, it sounds completely like science fiction, but this is the fundamental challenge. Silicon, the main ingredient in sand and rock, is the raw material we use. So how on earth do we take that and etch intelligence onto it? To understand how, we have to go small, like really, really small. Because everything, and I mean everything in the world of AI hardware, it all begins at the quantum level, with one single fundamental component. And here it is. Meet the MOSFET. The easiest way to think about it is like a simple light switch. But this is a light switch so incredibly tiny, you could cram billions of them onto the tip of your finger. And here's the crazy part. Instead of you flipping it, it can flip itself on and off billions of times every single second. Those flips create the ones and zeros that are the basic language of all computers. But, and there's always a but, when you shrink things down this small, physics starts to get, well, really weird and messy. As we get down to the atomic scale, all these forces start working against us. Electrons start to leak and go places they're not supposed to. Managing the insane amount of heat and power becomes this monumental engineering nightmare. It's a constant battle against these short channel effects, just to keep packing more and more power onto every chip. Okay, so having billions of tiny switches is amazing. It's a huge achievement. But that's just step one. How do you actually arrange them in a way that lets them do the ridiculously complex math needed for AI? Well, that's where the art of architecture comes in. This brings us to the AI processing engine. And the key idea here isn't just about doing things fast. It's about doing a huge number of things all at the exact same time. It's all about parallelism. And the secret sauce to making that happen is a concept called SIMT. It stands for Single Instruction Multiple Threads. The best analogy? Imagine a conductor in an orchestra. That conductor is the single instruction. And they're telling this enormous orchestra, hundreds of musicians, which are the threads, to all play the exact same note at the exact same time. That's how GPUs, the workhorses of AI, get their incredible power. And if you look inside the core of a modern GPU, it is just a masterpiece of efficient design. You've got things like Tensor Cores, which are basically these little mini factories built to do one thing and one thing only, the matrix math that AI absolutely loves. The memory is set up like a pyramid, with the fastest, most important data sitting right at the top, super close to the action. It's all about efficiency. Now, GPUs are amazing generalists, but the crazy demands of AI have pushed engineers to build something even more specialized. The goal now is to do one very specific type of calculation, but to do it faster and more efficiently than anything else on the planet. And that one crucial, all-important operation? It's the multiply accumulate, or MAC. It turns out that at their heart, neural networks are basically just gigantic, long chains of multiplication and addition. So these new AI accelerators are built with these massive grids of super simple calculators called MAC arrays that do nothing but multiply and add all day long at just unbelievable speeds. And this, of course, creates the next giant problem. You can have the fastest calculators in the universe, but they're totally useless if you can't get data to them fast enough. This is the infamous memory bottleneck, and it's a huge hurdle. But the solutions engineers have come up with are just genius. For example, instead of laying memory chips out side by side, high bandwidth memory, or HBM, stacks them on top of each other, vertically. They're connected by these microscopic tunnels called through silicon vias that create these super short, ultra-fast data highways straight into the processor. It's basically like building skyscrapers instead of a sprawling city to make the commute instant. So, we have the tiny components and we have the grand architectural design. Now for the really hard part. How do we actually build this impossibly complex thing? Believe it or not, it all starts as pure code, a text file describing the chip's logic. That code gets fed into a program that automatically translates or synthesizes it into a map of millions of logic gates. Then, more incredibly powerful software figures out the best possible way to physically arrange and wire everything together on the chip. And the final output of all this is a single file, the GDSI file. That's the master blueprint that gets sent to the factory to be manufactured. But turning that digital blueprint into a real, working piece of silicon means you are in a constant, brutal fight with the laws of physics. For example, the chip's heartbeat, its clock signal, has to arrive at billions of different spots at the exact same micro-instant. You have to build a power grid inside the chip that can handle huge surges without failing. And you have to figure out how to get rid of all the waste heat, or the chip will literally cook itself. So, to manage all this insane complexity, engineers use clever tools like something called the Roofline model. You can think of it like a diagnostic chart for a chip. It's a graph that shows them, visually, what the performance limits are. It tells them right away, hey, is your chip limited by its raw number crunching speed, or is it just sitting around waiting for data from memory? It lets them find and fix bottlenecks with incredible precision.
Okay, now let's zoom all the way out, because a single chip, no matter how powerful it is, just isn't enough for the kind of AI we have today. We have to think bigger. A lot bigger.
We have to go from thinking about a single piece of silicon to thinking about massive data centers. We're talking about linking thousands of these AI chips together to work as one single cohesive supercomputer. And that's when you get a machine that can actually change the world. And the scale of these systems, it's just staggering. To put it in perspective for you, running just one of these big AI training clusters for a year can use over 100 gigawatt hours of electricity. That is enough energy to power a small city. The amount of power these things consume is absolutely enormous. So, to keep scaling up, the whole industry is shifting its strategy. We're moving away from building one single giant monolithic chip, which is incredibly hard to do. The future is in chiplets. The idea is basically like building with Legos. You build smaller, specialized pieces, and then you connect them all together. It's way more efficient to manufacture, and it lets you mix and match the best technologies for each specific job.
So we've gone all the way from a single switch to a global brain. We've literally taught rocks how to think. It's an incredible story of human ingenuity. But it just begs the ultimate question. What comes next? What happens when we push beyond the limits of silicon?
And the future looks absolutely wild. People are working on wafer-scale engines, single chips the size of a dinner plate. They're exploring using light instead of electricity to do the math in optical neural networks. The quest to build better, faster, and smarter brains is just getting started, and it's pushing the very boundaries of what we thought was possible.